Now let's take a look at another concept or a technique which is used in the convolutional neural nets. This is used to reduce the dimension of the matrices as you progress in the network. As you can imagine, if you increase the filters, the number of matrices and their depth increases considerably, and so goes the same for their weights and biases. So that's a lot of parameters to handle. So there should be a way to make the calculations less intensive. So let's say this is one sample activation map which has 5 by 5 dimensions. So what we're going to do now is for max pooling layer, you're going to take the biggest number in a specific region, right? So this region can be decided by you. So this could be a 3 into 3 area, or it could be a 2 into 2 area, or it could be a 4 into 4 area. So in this 3 by 3 area, what you see here is that the highest number is 6600. So that's what we're gonna get here, 6600. So now if I just move one column and take the next 3 by 3 matrix here, the highest number is 785. So you're gonna get a 785. Now if I move another column and I take these 3 by 3, then the highest is 1200. Now if I just move one down, if I take this 3 by 3 matrix, the highest number is 2542, and then so on, and then I go one down further, and then I move one column at a time. So if I move one column at a time, that's called the stride of 1. If I move two columns at a time, that will be a stride of 2. It basically tells you how fast you're moving in the matrix. So this is your output matrix of the max pooling layer. Now pooling layer are of different kinds. You have average pooling layer, you have minimum pooling layer. Great. So this is the technique used to reduce your matrix size. Now let's take a look at another technique. So as you have noticed, when you use a convolution filter of a 3 by 3, let's say on a 5 by 5, the output is a 3 by 3. So it means that the output of a convolution operation is smaller than the input size. Now this does not pan out good in some use cases, and this leads to feature dilution. So in order to protect from that, you can pad the input matrix with zeros. So now your 5 by 5 matrix will become a 7 by 7 matrix. And now if you use a convolution filter of a 3 by 3 matrix, so 7 minus 3 is 4, 4 plus 1 is 5. So your output matrix size will be a 5 by 5, which is the same as the original 5 by 5 before the padding. So hence you can keep the size of the input and the size of the output after the convolution operation to be the same. Perfect. So the last layer is a fully connected layer. So much like what we've seen in the feed forward network. So you have a hidden layer and the input neurons are fully connected to the hidden layer, and then this is fed to a output activation function like softmax.